we want to compare the wavelength of an electron traveling at 5.0 times 10 to the 7 meters per second and a 4.50 gram bullet going 950 meters per second. Okay, so we're going to use this equation, which is called the de Broglie equation, after a Frenchman named Louis de Broglie. It actually gives us the wavelength associated with a certain mass moving at a certain velocity. So we have an electron that's traveling at 5.0 times 10 to the 7 meters per second, very, very fast, and a bullet, which is 4.5 grams, and it's going 950 meters per second, also very, very fast. We want to see what the wavelength is associated with that. What's the wave-like property of that particle? Okay, so let's go ahead and calculate the wavelength of the electron. So it is going to be Planck's constant, 6.626 times 10 to the negative 34 joule seconds. Oh, actually, we can't use the joule here. We have to remember, here is why. We have to make sure that our units actually work out. So this is going to be lambda. Our unit has to be in meters. So if we recall, the joule is a derived unit. The joule is equivalent to kilograms meters squared per second squared. So a joule second, is equal to kilogram meter squared per second, right? Joule second, the second on top cancels one of the seconds down below, so that is the unit. So it's going to be kilogram meter squared per second. Now that means that mass has to be expressed in kilograms because the units have to match. So the mass of an electron, when we look it up in a table, it is equal to 9.1 times 10 to the negative 31 kilograms. It's actually in the back of your book. And the speed is 5.0 times 10 to the 7th meters per second. So here we go. Kilogram cancels kilogram. Meter cancels 1 meter. Second cancels second. Sure enough, we're left with a unit of meters. So everything works out just fine. Well, the wavelength of the electron happens to be 1.45 times 10 to the negative 11. 10 to the negative 11 meters. And if you want to take a look, that's on the order of the length of the wavelength of an X-ray, which is actually going to be important in just a minute. So now let's go ahead and do the wavelength of the bullet. So the wavelength of our bullet is equal to 6.626 times 10 to the negative 34 kilogram meter squared per second divided by the mass, which again has to be in kilograms. So 4.5 grams is 0.0045 kilograms. And we said it's traveling at 950 meters per second. Very, very fast. Meters per second. So second cancels second, meter cancels one of the meters, kilogram goes with kilogram, and what you end up with is 1.5 times 10 to the negative 34 meters. So there you go. You have a bullet that's a standard bullet, 4.5 grams. It's traveling at 950 meters per second. There's actually a wave associated with the energy that's, I'm sorry, it's not a measure of the energy of the bullet. That's different. That is, kinetic energy, 1/2 the mass times velocity squared. This is different. This is the bullet. Instead of thinking about it as a particle traveling through space, we're thinking about it as a wave traveling through space. Now that wave does damage. It does damage as a particle, but there is a wavelength associated with it. The reason that we don't actually experience that wavelength, or some of the properties associated with this wavelength, is because the mass of the bullet is so big and this is so immeasurably small that it goes virtually unnoticed. However, it does prove that, it goes to show that a particle does have wave-like behavior, just like a wave, which is pure energy, has particle-like behavior. And this is the great, I don't know what to call it, the great unique thing about quantum mechanics is that as you get smaller and smaller and deal with smaller particles at the atomic and molecular level, are you talking about a wave? Are you talking about a particle? What's going on? Are you talking about pure energy, or are you talking about actual mass? Well, both. They're just, different sides of the same coin. So let's make some observations and we'll go ahead and close off this discussion. 1.45 times 10 to the negative 11 is on the order of the wavelength of an X-ray. Is on the order of the lambda of X-rays. As it turns out, shooting a beam of electrons, now an X-ray is a wave. It's light. It behaves as light, and light has certain waves behave in certain ways that particles don't. All of classical physics is based on the fact that waves behave one way, particles behave another way. So waves, so now shooting a beam of electrons at a crystal gives a similar pattern to the diffraction pattern seen when X-rays strike the crystal. When you shine X-rays at a crystal, the spaces in between the crystals actually take the light, which is in the form of X-rays. Light is our general term, right? We're not talking about visible light. And it actually diffracts it, and it gives you a particular pattern. Well, that pattern is unique and tells you what the structure of the crystal is. That's how we get molecular structures for all the biological molecules, that we actually know what they look like. We actually crystallize them. We shine X-rays at them. Well, here's what's interesting. This diffraction pattern is characteristic of waves, not characteristic of particles. Particles don't do this. Waves do this. Diffraction is a wave property, not a particle property. Well, check this out. When I take a beam of electrons, which are particles, we know that they are particles, and we shine them at the crystal, guess what happens? We get the same diffraction pattern. That's very, very odd. That confirms the fact that particles behave like waves. So, a particle, which in this case is the electron, behaves like a wave. Okay. So this was our general discussion. I'm going to go ahead and stop the discussion here, and next time we'll go ahead and pick it up with a discussion of electrons in atoms, with an introduction to real quantum mechanics, and talk about electrons and how they behave. So, but I definitely wanted to get a good foundation here for light, how it behaves, the idea of wavelength, the idea of frequency, and the idea of energy being quantized. The big word is quantum, and that just means packet, the Latin word for a little package. So the idea is that energy is quantized. Energy rises and falls in discrete units. It does not rise or fall continuously like some functions that we're accustomed to seeing. It's very, very discrete. It's a stair-step function is what it is. So with that, thank you for joining us here at Educator.com. We'll see you next time. Bye-bye.